Hey guys, this is a little video I'm making about the labs for Unit 1, Heat and Thermodynamics in the second semester of physics. Had some questions about how something worked. I'm not really sure what the question was, so I just thought we'd kind of run through the whole thing, and then whatever part you need, you can get that. So I've got a number of things open here. This is the little packet that of questions that we're using. If you don't have a packet, if you're in my other classes, then these are the three labs that I've asked you to pull up. And so let's just take a look real quick and see what it says. The first sim, there's a link that this is down not in the first item here, but down in thermal expansion lab. It says click this link right here. Well, I've got that pulled up, so this is that. It says there is a metal bar right here above a burner, and you can turn the fire on right here, and you saw the little fire. See how the needle goes up? Basically that bar is heating up, and as it does, the rod gets a little bit longer. It pushes right there, which angles up that needle. You can push the red button at different times, and you can get up to 5 different temperatures. And so that's what they want us to do here, and the reset sets it all back. So what they want us to do here is to push reset, change the slider to turn on the heat, and observe as it heats and the needle swings upward. Notice the needle's speed, how fast it's going, that is. When the needle reaches 50, push the red temperature button, and we're going to work out the thermal expansion coefficient here. So I'm turning it on. We're watching the needle. When it gets all the way up here to 50, I'm going to push the red temperature button, and that will give us the number that we want. The formula is there in the procedure. All of this is in the procedure, but normally we write delta L equals alpha L naught delta T. Here we don't know L naught, so we're kind of rolling alpha and L naught up together. Here comes 53, 2, 1, click, and it looks like that was about 38.7 right there. So that is the delta T. We started at 0 and it went up to 38.7 when the needle here went from 0 to 50. So they just simply want you to take that. You're going to put in 50 for the delta L, and the delta T is the 38.7, and you divide, and you've got this letter A, which would be the product of alpha and L naught. We never know what they used for L naught, so that's all you can do. All right, push and reset here. Question number 2. Oops, you know what? I was supposed to, what they want you to do is to turn the fire off. So let's say that it heats up all the way, and then I could reach over. I'm going to let it go to 10 this time, and I turn the fire back off. Okay, the fire went off, and the rod's going to start contracting down there, and there's a couple questions about how it does that. Does it contract at the same speed that it expands? Well, you're adding a whole lot. You got a fire underneath this thing, so it's going to heat up really fast, but now it's just radiating heat, and that's a slower process, so the needle's coming down slower right there. Number 3, they ask you to take 5 different times. So I'm going to turn the heat on, and when it gets to 10, I'll push the red button, and same thing at 20 and 30 and all the way up to 50. Here we're getting 5 data points, and they want us to actually plot those on a spreadsheet. So I'll grab a spreadsheet here in just a second as soon as I got some data. That was a little bit early, sorry. What's going on with my temperature here? Yeah, temperature broke. I didn't push reset. Let's try that again. But we want to get those 5 temperatures there, and something jammed up and I didn't push reset. Okay, that's looking better. All right, here comes 30 right there, and 40. Isn't this fun? We would be doing this exact same thing in the lab, except we'd be using steam with the risk of getting burned somewhat. So there are my numbers, and what they want us to do is to go get a spreadsheet. So I'm going to open up a spreadsheet here. I don't know how much of this you've done in the past, but it's one of those things that you really need to know how to do. It's a good job skill, and So I'm going to open up just a regular spreadsheet here and try to size it down to where we can see the numbers and the stuff. It says in the first column, type the delta L values. So I'm going to start a column here, and remember the delta L are these, so I'd put 0 and 10 and 20 and 30 and 40 and, oops, covered it up, 40 and 50, like that. Okay. And then in the second column, they want us to put the delta T column. So right here, I've got 7.7 and 15.6. Just grabbing the numbers that we just took. Anytime you collect data, if you can make a picture of it, it brings out all of those 38.8. You know what I did? I shouldn't have put the 0 in there. We have 5 numbers, and the first one came about when we copy, delete. There we go. First one came about when we got to 10. Oh shoot. I don't know what this thing's doing. Let's delete it from there. Let's move it down here. Ha! Alright, fine. I'll do it this way. Grab these guys and drag them up there. And where'd it go? Mercy sakes. So there's my data, right? And that's what they ask you to do in the directions of this thing. We have now put the delta L and the delta T values. We select all 10 with the data, and we want to insert a chart and add a scatter graph. So let me show you what that looks like real quick here. Come on. I'm going to select all 10 of these like that. I'm going to go over here to the insert menu, click on that, and it should change. And we want the scatter graph, which would be this one right here. Okay. You can say, show me the dots, show me the line with the dots, just the line. Doesn't really matter, just pick something. See how that's a nice straight line right there? That's what we want to know. What does our data look like? What is the trend? What's the pattern? Is this a linear function? And just looking at the formula, delta L equals constant times delta T. That's a linear function. Now, if I had delta T squared or cubed or the square root or exponential or logarithm or sine, then it would do something else. But that shows that this is a nice linear function. It's going to make a nice straight line. So that's what we're trying to do. And they ask about that in number 3. Similar thing that we do here back on the lab. They want us to hit reset, hit start again, turn the fire back on. This time we're punching a stopwatch function. You've got one of those on your phone. You can get a little stopwatch if you want. You would have taken the time there at 10, 20, 30, 40. Draw that same graph and see what's happening with that. Then there's a couple more questions. So that's not a big deal. You can do that. I'm going to go down here and grab the next lab, which is the calorimetry lab. It should look like this, and let's just kind of see what's up with this one. There's a burner underneath here, okay? And I've got a block of something. Right now that's zinc. It's 60 grams of zinc, but I could change the mass of the zinc, how much ever I want that to weigh. I can also change the material to whatever I want. And so let's say I've got 80 grams of lead in there. I put this chunk of metal in the water. When I turn the burner on, it's going to start here at 0, and you can see that the water is heating up very fast. The water is going to heat that block of metal up. And so what we're doing here is we're saying I've got that much metal, and it's going to eventually get the same temperature as the water. We're pretending it kind of happens instantaneously. And right there at 100, the water boils. So the water doesn't get any hotter. You can't heat water above 100 unless you've got it contained. Otherwise, it's going to turn into steam and boil off. So you end up with less water. But I've heated that block up to 100 now. Now over here in the calorimeter, this is a device that measures temperature. So you got water in here. We're going to take the lid off, and there's water in there. How much water? You can change it how much ever you want there, and they give you some recommendation in the thing. You can make that temperature just about anything from 4 up to about 20 degrees. That'd be about room temperature there. Let's go a little bit less than that. It doesn't matter. But right here, this thing is going to slide that block over into the calorimeter, and as soon as the calorimeter gets the block, then the heat from that hot block goes into the water, and this temperature starts to rise right there. And what we want to do is watch and see what the highest point that it reaches is. So that's all that is up with the specific heat lab. Now, of course, you know that we've got a formula that governs how this does as well. I'll put the first one here. We didn't really write it down, but what we want to do, where's my writing controls? Dang, nabbit. Is to use our sensible heat formula here to get, here it comes, this thing lined up. So for that first lab, thermal expansion lab, we had a formula. Normally is delta L equals alpha L naught delta T. We wrap these two variables together. So delta L equals A, some constant, which is now the product of these two constants, delta T. And we wanted to solve for that, and we did that. Big deal. Okay. This one right here is specific heat lab. And we have a formula that tells us how water changes temperature. And of course, Q equals mc delta T. This would be the mass of the object, the heat capacity or specific heat, the C of that material. You got to know, is it water or gold or glass or whatever. And this would be the change of temperature there. Now this is a mixing problem that we're doing. And when you mix, I need to make sure that the sum of the heat is equal to 0. So I've got two things that are gonna happen. The water is going to heat up, and the block of lead or whatever you have in there cools off. But when I add those together, I'm going to get 0. All right. Well, water heats by this formula, mc delta T. So I'm going to put that right here. And I'll put some little subscripts, m sub W, c sub W, delta T sub W, kind of help with that. The lead is going to change temperature also. So that's another sensible heat change. And we'll put m sub L, the mass of the lead, times c sub L, the heat capacity of the lead, delta T of the lead equals 0. Okay. Now, there's a bunch of constants in here, and you got to keep all these straight. So let's go back to our picture here where we had this. And remember, we had 160 grams of water at, I think it was 17 degrees. Okay? We'll say that's what it was. I should have written all this down at the beginning, but the mass of the water, 160 grams, and the heat capacity is 4,184. That's a constant that we just use all the time. And this is joules, kilogram, degrees Celsius. And the temperature of the water initially was, I think, 17 degrees Celsius. All right. I also got to have the numbers on the lead. So the mass of the lead was, what do we have? 80 grams. We took it up to 100 degrees. And we'd like to know what that thermal constant is, what that specific heat is. Mass of the lead, 80 grams. Heat capacity of the lead, don't know. That's what we're looking for. And the temperature was 100 degrees before we put it in. What we can do now is look back at our lab and say, well, what was the final temperature right there? And the final temperature looks like 18 degrees. So we'll put that in right here. And so we've got everything that we need. The one that we want to solve for is this. So I'm going to subtract this from both sides. which will give me MLCL delta TL equals negative MWCW delta TW. And then I can divide both sides by the mass of the lead and the delta T of the lead and get that heat capacity by itself. And that's what we want to put our numbers into, and we've got them all up there. And we do that and we solve. Remember that this change of temperature is always the final minus the initial. So like the final was 18, and the initial for the lead was 100. So I'd want to set it up like that. For the change of temperature of the water, final minus initial, it stopped at 18, and it started out, I think, at 17. I should have looked a little closer at that. The heat capacity of the water is 4186 joules per kilogram degree Celsius. The mass of the water was, what was that, 160 grams. Let's see how you just kind of fill in the blanks here. Okay. And then lastly, we had the mass of the lead right here would be 80 grams. Now, probably should change those to kilograms. Here it's okay, it doesn't matter. See how I've got a gram on the top and gram on the bottom, so those are going to cancel out. If I went to the trouble to translate them into kilograms, it would still cancel out and be all right. All right. I've got this degree Celsius on the bottom. It's going to cancel this one on the top. The only units left will be joules per kilogram degree Celsius, which are the proper units for C. So this came out fine. We just get the number, and that'll be the C, the heat capacity of the lead. All right, that's the kind of thing that we want to do there. And if we were meeting in lab, we would do exactly the same thing here. They ask you to draw a little graph there, so it's the same process. You know what? I didn't scroll down the wrong page. I've got two of these open. Mix and transfer. All right, I don't think we're doing a graph on this one. So they tell you what to put in there. You do it. You find the final temperature. This is the video. I'm sorry, that's the lab. Here we go. Pull up the sim. Walks you through the controls and everything. Ask you some questions just to make sure you got the right place. Set it up like this. That's what we did. This is aluminum, 60 grams, all that. Just run it like it says. Solve for the heat capacity. We did that. Okay. Hit reset, find the specific heat of gold. All right, so there's a number of these. Right here, this is a calorimetry problem. If you're changing 1 kilogram of water 15 degrees, you've got the number, you multiply it out. The 2 kilograms of iron and 450 is C there. Change it 30 degrees, you can multiply them out. Which one's more, right? So that's that. Not too bad, not too bad. Here's the third lab, the gas property lab, and this one is actually a PHET right there. It looks like that. And you can interact with this in the same way that you did on the other one. So it says give a couple pumps of air. Right here's a little air pump, and you go foof, foof, and now you've got some air in that box. Previously it was just vacuum. There was nothing in there. But you can see that the pressure came up, and now it's recording a temperature. There was nothing before, so it's kind of hard to measure the temperature. And you just kind of go through here and answer the questions. You can see some of those are slow and some are fast, and they're always colliding. And that's a pretty good picture of a gas right there. If we could zoom in on the molecules of gas, that's very much what it would look like. They'd be bouncing off of the walls, bouncing off each other. Those are perfectly elastic collisions, so there's no loss of kinetic energy there. No loss of momentum, of course, because we never lose momentum, but you know, they just keep doing what they're supposed to be doing. And it asks you to do a couple things here. There's some controls over here. Hold something constant. You got a stopwatch you can pull up, you know, and push go here if you need to. Well, I haven't seen this. How many times does it hit the wall? So it's counting every time a ball hits the wall, right? That's interesting. Oh, you can set the sample. So the more collisions per second, then that's going to translate into a more force transferred to the wall, more momentum, more pressure there over, force over area is going to be pressure there. So you can do all kind of things. You can come down here and add heat. You can add ice. That's going to cool it off, and do whatever you need to there. You can change the volume of the gas. I'm going to change the volume, see how the pressure went up and the temperature went up. So this is a pretty good way to get your head around what happens with an ideal gas law. If I expand it, the pressure drops and the temperature drops. If I add heat, then the temperature is going up and the pressure is going up. And if you let it go long enough, why, then the pressure will get high enough, and you'll actually, come on now. I should have closed it down first. But see how fast those molecules are jumping around? They have a lot more energy now. Boom, just blew the lid off the thing. And that's what happens in real life. If you put too much pressure on something, it will blow. So yeah, some of those kind of problems. And those are the 3 labs that you have here. Again, I'm not sure what the question was, so I have no idea if I answered it properly, but hopefully that helps you get started with it. And if not, just send me a note and we will see what happens. Thanks so much. Have a good day.